Hello. Today's lecture is on the method of variation of parameters. This method tries to find a particular solution for an nth order linear inhomogeneous ODE. So we assume we have an nth order linear inhomogeneous ODE of the following form, and we assume that we already found the complementary solution, or if you want, the general solution of the corresponding homogeneous ODE, and the goal is to try to find the particular solution using some robust procedure that will always give us a particular solution irrespective of what this function f of x is, and we do not want to use the method of undetermined coefficient. So what we'll be doing is we're going to define this procedure, which is called the variation of parameters, for first second order ODEs, and then we're going to generalize it for nth order ODEs. So why aren't we gonna do it for first order ODEs? Because recall that first order linear inhomogeneous ODE, we know how to solve it. You learned that before in the previous chapters. The idea is to write it in standard form, where y prime is multiplied by 1 only. And then we're going to find the integrating factor, multiply the whole ODE by the integrating factor, which means that the left hand side is equal to the derivative of y times the integrating factor, and this implies that we can integrate both sides to deduce at the end what y of x is. Now note that in this case, if f of x from the very beginning was equal to 0, meaning that if we want to find the solution of the homogeneous linear first order ODE, this implies that this term is equal to 0, meaning that the first term, which is c1 over the integrating factor, is actually the solution of the corresponding homogeneous equation. So this is nothing but my complementary solution, which is c1 y1. So I'm going to call 1 over the integrating factor y1, and this implies that the second term is my particular solution. And note that the form of my second term is y1 times some function, I'm going to call it u1. So for first order linear inhomogeneous ODEs, no need to find first homogeneous solution, then particular solution. We can directly solve the inhomogeneous ODE by multiplying it by the integrating factor, but we still get the same form, a complementary solution and a particular solution. So we're going to go to second order linear inhomogeneous ODEs, and I'm going to assume that my second order ODE is written in standard form. Recall, in standard form, this means that the highest derivative of y is just multiplied by 1, so we do not have a function in here. So you have to make sure to write your ODE in standard form. And the assumption is that we already found the complementary solution, which is the solution of the corresponding linear homogeneous ODE. So we found it, and we would like to find the particular solution, because the general solution of this ODE is nothing but yc plus yp. Fine. So the idea is similarly to the first case where the particular solution was nothing but y1 times a function. So what we're going to do with the idea of the method of variation of parameters is to assume that the particular solution is nothing but some function u1 of x multiplied by y1 plus some function u2 of x multiplied by y2, where in this case y1 and y2 form the fundamental set of solutions for this second order linear ODE. So I'm going to assume that yp is of this form, and the goal is to find what those two functions u1 and u2 are. So I want to find what u1 and u2 are so that we can define yp. The way to do it is that we're gonna differentiate yp once and twice, so we're going to find yp prime and yp double prime and plug them in the inhomogeneous ODE and try to find some relation between my unknowns so that we can deduce them. Note that in here yp prime, to find it, we're going to use the product rule of differentiation. So it's u1 prime y1 plus y1 prime u1. Similarly, for the second term, it's u2 prime y2 plus y2 prime u2. So we get the following four terms for yp prime. And to find yp double prime, this is nothing but the derivative of yp prime. So I'm going to take those four terms, differentiate them. So we're going to differentiate each term. We're gonna apply also the product rule. So it's gonna be the derivative of u1 prime times y1 plus y1 prime times u1 prime, and so on. So after we find the derivative of each of those four terms, we're gonna get that yp double prime is equal to those six terms in here. So we're gonna take those values, plug them in our inhomogeneous linear second order ODE. So I'm gonna take yp double prime, which is those six terms, plus p of x times yp prime, those four terms, plus q of x times yp, which is nothing but u1 y1 plus u2 y2. All this should be equal to f of x. Okay, so it should be equal to f of x. So now what I'm gonna do is I'm gonna order the terms. First I'm gonna pick the terms that are multiplied by u1, which are shown in red, and I'm gonna factor u1 out. So I'm gonna get u1 times y1 double prime plus p of x y1 prime plus q of x y1. Note that since y1 is a solution of the homogeneous ODE, so this implies that this term in here in red is nothing but 0. It's equal to 0. Similarly, I'm going to take the terms that are multiplied by u2, where we have y2 double prime u2 plus y2 prime u2 multiplied by p of x, plus this term in here. I'm going to factor u2 out, and I'm going to get y2 double prime plus p of x y2 prime plus q of x y2, which is also equal to 0. Why? Because y2 is also a solution of this homogeneous ODE. We're left in here with two terms, so I'm going to put them in. And we're left with those four terms. Note that if I take the first term and y1 prime, u2 prime, this is nothing but the derivative of u1 prime times y1. And similarly, if I take this term and u2 prime, y2 prime, this is nothing but u2 prime times y2 all differentiated. So I added those two terms in here, and I'm left with one term, one u2 prime, y2 prime, and u1 prime, y1 prime. I add them in here, and all this is equal to f of x. So after simplifying the first two terms, I'm left with the following form. Recall that our goal is to find u1 and u2. So in here it's obvious, the terms that are left, we have u1 prime, u2 prime, u1 prime, u2 prime, and so on. So our goal is at least to find what u1 prime and u2 prime are. Once we find them, we can deduce what u1 and u2, the value of those two functions is. So, but I have just one equation with two unknowns, which are u1 prime and u2 prime. To be able to find my two unknowns, I need two equations. So based on this equation, this formula in here, what we can, let's say, think of is if I assume that this term in here, which is repeated in here, so if I assume that y1 u1 prime plus y2 u2 prime is equal to 0, then this formula will be reduced into a simple linear one in u1 prime, and I'm gonna get another solution another equation in u1 prime u2 prime. So if I assume this is equal to 0, which I put it as my first equation, then I'm gonna get the derivative of 0 is 0. I'm gonna get the second equation to be y1 prime u1 prime plus y2 prime u2 prime equals to f of x. So now I have two equations with my two unknown functions u1 prime and u2 prime. And with those two equations, we can find what u1 prime and u2 prime is. But the question is, will the system always have a solution? So can we find what u1 prime and u2 prime are? Recall from linear algebra is that this system can be written in matrix form. So we can write it as the matrix y1, y2, y1 prime, y2 prime multiplied by the vector of unknowns u1 prime, u2 prime equal to the right hand side vector, which is 0 f of x. So those two are equivalent, one in equation forms, the other in matrix form. So the question is, does the system of linear equations have a unique solution? Recall that it has a unique solution if and only if the determinant of this matrix is not equal to 0. So what is the determinant of this matrix? The determinant of this matrix is nothing but the Wronskian of y1, y2, right? And recall that this Wronskian is never equal to 0 because y1, y2 forms the fundamental set of solutions for my second order linear ODE. So they are linearly independent. So this implies that we know for sure that our system has a unique solution, so we'll be able to find what u1 prime and u2 prime are. Fine. So you can solve this system either using the equations or in matrix form. You can solve it whichever way you prefer, but simple to solve. It's just two systems of two equations and two unknowns. So at the end, we're gonna solve for u1 prime, u2 prime. Then to find u1 and u2, we're gonna integrate the equations. We're gonna get something of this form. So I denoted u1 prime to be equal to some function w1 and u2 prime equal to some function w2 after solving this system. One note about the constants C3, C4. We may assume at this stage that they're equal to 0, and this will not affect our general solution, the general solution of the inhomogeneous second order ODE. Why this will not affect the general solution? Because I'm going to assume that I'm going to keep those two constants. Recall that yp is u1 times y1 plus u2 times y2. So I'm going to get this. It's equal to c3y1 plus c4y2 plus those two terms. So if then I deduce what y of x, the general solution is, which is the sum of the complementary solution plus the particular solution. The complementary solution is the solution of the homogeneous ODE, the corresponding homogeneous ODE that we know, which is c1y1 plus c2y2. If I add this term and this term, so I'm going to get c1 plus c3y1 and c2 plus c4y2 plus my two antiderivative terms. Fine, but recall that c1, c2, c3, c4 are arbitrary constants, so I can rename this sum as C1, big C1 or uppercase C1 times Y1 plus uppercase C2 times Y2. Okay, so which implies that if I assumed from the very beginning that C3 and C4 were equal to 0, I'm going to still end up with the same general solution form, okay, rather than uppercase C1, lowercase c1, but it doesn't matter because all these constants are arbitrary constants. Okay, so that's why whenever we find what u1 and u2 are, we're going to assume that the constants are equal to 0 for simplicity. it wouldn't change the form of the general solution. Now, true, the particular solution will be different, but recall that what we need to find is a particular solution, one particular solution, and particular solutions are not unique. Okay, fine. So now we know how to solve how to find particular solutions using the method of variation of parameters. We're going to consider the following example. So I'm going to assume that I have the second order linear inhomogeneous ODE y double prime plus y equals tan x, where the assumption is x is in the open interval minus pi over 2 pi over 2, and I would like to solve this ODE. I want to find its general solution. So since it's a linear ODE, its general solution is the solution of the corresponding homogeneous equation, we're denoting it by YC, plus a particular solution. Now, we're going to find the particular solution using the method of variation of parameters, but to be able to do so, we first have to find the what's called the complementary solution, i.e. the solution of this second order homogeneous ODE. Note that this is a second order ODE with constant coefficients. So to find its solution, first thing we need to do is define the characteristic equation or the auxiliary equation, which in this case is m squared plus 1 equals to 0. Which means that the roots of this equation are plus or minus I. So it's a complex root. We have two roots, complex conjugate, where alpha is equal to 0, and I'm going to consider beta to be equal to 1. As we mentioned before, it doesn't matter if it wouldn't differ if you consider beta to be equal to minus 1. So this implies that my complementary solution is going to be C1 cosine of x plus C2 sine of x. Recall, for in the case where you get two complex solution, two complex roots, the solution is of the form C1 e to the alpha x cosine beta x plus C2 e to the alpha x sine beta x. So that's why we got the following form. So we found our homogeneous, the solution of the homogeneous ODE. We found the fundamental set of solutions, which are cosine x and sine x. Now we can use them to find a particular solution. So by the variation of parameters technique, or the method of variation of parameters, I'm going to assume that my particular solution is some function u1 times y1, which is cosine of x, plus a function u2 times y2, which is sine of x. So u1 and u2, they satisfy the following two equations. So we have y1 times u1 prime plus y2 times u2 prime equals to 0, and then the second equation we have the same unknowns, u1 prime, u2 prime, but y1 and y2 are differentiated, okay, and we set it equal to f of x. So we already know what y1 and y2 are, so we can plug them in. y1, we're denoting it by cosine x, its derivative is minus sine x. y2 is sine x, its derivative is cosine x. As for f of x, note that to define it correctly, recall that the ODE has to be written in standard form. Okay, so in here our ODE is already in standard form because y double prime is multiplied by 1. But if you had any other constant or function in here, you cannot define f of x before dividing by whatever multiplies u double prime. Okay, so in this case f of x is tan x, but in some other cases, the ODE might not be written in standard form, so make sure to first write it in standard form and then define f of x. So fine, now we need to solve this system. The way I'm gonna solve it is I'm gonna first find u1 prime in terms of u2 prime. So note that u1 prime is nothing but minus sine x over cosine x u2 prime, or if you want, minus tan x of u2 times u2 prime. Then I'm gonna plug in, I'm gonna replace u1 prime in the second equation, so that I get in here a term which only depends on u2 prime, which after taking common denominators, note that in here I have cosine squared plus sine squared, which is equal to 1. So I have u2 prime over cosine x equals to tan x, and this implies that u2 prime is cosine x times tan x, which is nothing but sine x. Fine, so we found what u2 prime is. Now I need to plug that back into this formula in here so that I can deduce what u1 prime is. So this implies that u1 prime is equal to minus sine squared x over cosine x. So the next step would be to integrate those two formulas in here and find what u1 and u2 are. So first we need to integrate minus sine squared x over cosine x. Recall the antiderivative of this term is some constant c3 minus the antiderivative of sine squared x over cosine squared x. So we're gonna pull a few tricks to try to integrate it. So sine squared x is nothing but 1 minus cosine squared x. So I'm gonna get in here constant c3 plus the antiderivative of cosine x minus the antiderivative of 1 over cosine x. Now this antiderivative, we know it's sine x. This 1 over cosine x is actually nothing but secant x. Its antiderivative is not trivial, but the trick is to multiply and divide by secant x plus tan x. Why are we doing so? Because it so happens that the secant squared of x plus secant x times tan x is the derivative of secant x plus tan x, meaning that in this case we're going to get derivative of secant x plus tan x over secant x plus tan x, which will be nothing but minus ln of absolute value of secant x plus tan x, or if you want you can write it as sine x plus 1 over cosine x. Okay, so the u2, finding u2 is simpler, because in here we're going to get c4 plus the antiderivative of sine x, which is minus cosine x. As I mentioned before, for simplicity we're going to assume that c3 is equal to c4, which is equal to 0, and then I'm gonna plug u1 and u2 back in the definition of yp. So I'm gonna multiply u1 by cosine x and u2 by sine x, with the assumption that c3 and c4 are equal to 0, and note that the first term is sine x cosine x minus sine x cosine x, so it cancels out. So I'm left with minus cosine x times ln of absolute value of secant x plus tan x, or you can write it in this form. So finally we can deduce the general solution of this inhomogeneous ODE, which is the complementary solution plus a particular solution. In this case it's going to be a constant c1 plus times cosine x plus c2 times sine x minus cosine x ln of this term, absolute value of secant x plus tan x. So now we move to higher the extension to higher order linear inhomogeneous ODEs. So I'm going to assume that I have an nth order linear inhomogeneous ODE written in standard form. So the assumption is that the highest derivative, the nth derivative of y, is just multiplied by 1. If it's not, then note that you have to divide by whatever is multiplying the nth derivative to write it in standard form. So the general solution of this inhomogeneous ODE is the complementary solution, which is the general solution of the corresponding homogeneous ODE plus a particular solution. So we're going to assume at this point that we already know the complementary solution. So we have already found the fundamental set of solutions y1, y2, y3 up to yn. And our goal is to find a particular solution. So the idea of the method of variation of parameters is to assume that the particular solution is of the form u1, some function u1 times y1 plus a function u2 times y2 up to un times yn. So we're gonna, if you want to replace the constants in the complementary solution by functions u1, u2, un. And we're gonna do the same procedure as we did for the second order linear inhomogeneous ODE. So we're gonna differentiate yp not just once and twice. We're gonna differentiate it n times, plug it in this inhomogeneous ODE, and try to deduce n equations, in this case, containing u1 prime, u2 prime up to un prime, yn, because now my unknowns, I need to find n unknown functions u1 up till un. So to be able to find those functions, I need n equations. It so happens that the equations are going to follow the same pattern that we noticed for the second order. Recall, for the second order, the first equation we had u1 prime, u2 prime. The first equation had y1, y2. The second had the derivative of y1, y2. So in here we're gonna have a same pattern. So the first equation is gonna be y1 times u1 prime plus y2 times u2 prime up to yn times un prime. So my unknowns are u1 prime, u2 prime up to un prime. So this is my vector of unknowns. The second equation is gonna be we're gonna have the same form, but instead of u1 up to un, I'm gonna have the first derivative of u1 up to un. The right hand side is 0. So I'm gonna keep on differentiating my y's, my fundamental set of solutions in this formulae up to the n minus 2th derivative. Okay, so we're gonna end up with n minus 1 equations, where I have each equation. So the ith equation has the ith derivative. Ith equation has the I minus 1th derivative of y1, y2 up to yn, and they're all equal to 0, except for the last equation we have the n minus 1th derivative of y1, y2, yn, and this left hand side is set equal to f of x, the function in my right hand side of the ODE in standard form. So the question that we ask now is, okay, we have a system of n equations and unknowns, but does the system have a solution? The answer is, by writing it in matrix form, we know that this system has a unique solution whenever the determinant of this matrix is not equal to 0. What is the determinant of this matrix, if you note? This is nothing but the Wronskian of y1, y2, y3 up to yn. and meaning it's the Wronskian of the fundamental set of solutions. And this Wronskian is not equal to 0 because we already know that the fundamental set of solutions is a set of linearly independent solutions of the corresponding homogeneous ODE. So the Wronskian is not equal to 0. So this system has a unique solution. So eventually we will be able to solve this system and find the values or the functions that are equal to u1 prime up to un prime. Now in practice you will not be asked to solve a system of equations where n is larger than 3. So we're going to consider n equal to 2 or n equal to 3, not larger n values. So I'm going to consider the following example. I have the ODE y triple prime plus y prime equal to tan x, where x is between minus pi over 2 pi over 2. So this is a third order ODE. And similarly to the second order ODE, the first thing that we need to do is find the solution of the corresponding homogeneous equation. So we need to find the complementary solution. So first I'm going to solve y triple prime plus y prime equals to 0. So this is also third order linear homogeneous ODE with constant coefficients. So we're going to find the characteristic equation, which is equal to m cubed plus m equals to 0. Note that in here it's easy to factor it out. We're gonna have m into, sorry, there's a typo in here. It's m squared plus 1. So m into m squared plus 1. So the roots of this equation are m equals to 0 and m squared equals to minus 1, which implies that m is equal to plus or minus I, where alpha is equal to 0 and beta equals to 1. So we're gonna get in here the set of the fundamental set of solutions where y1 is e to the 0x, which is 1, y2 is equal to cosine of x, y3 is equal to sine x. So my complementary solution is c1 times y1, which is 1, plus c2 times y2, which is cosine x, plus c3 times y3, which is sine x. So we have found the complementary solution. Now, by the method of variation of parameters, I'm going to assume that the particular solution is u1 times y1 plus u2 times y2 plus u3 times y3, which in this case is u1 plus u2 cosine x plus u3 sine x. And I need to set my system of 3 equations and 3 unknowns. So note that when n is equal to 3, I'm going to have 2 equations which are set equal to 0, and the last equation, it will be set equal to my right hand side function f of x, where the ODE is written in standard form. So we start by the first equation having y1 u1 prime plus y2 u2 prime plus y3 u3 prime equal to 0. The second equation will differentiate y1 y2 y3, but we still set it equal to 0. And the last equation we have the second derivative of y1 y2 and y3. Okay, so we know what y1 is. y1 is 1, y2 is cosine x, and y3 is sine x. The derivative of 1 is 0. So the derivative of cosine x is minus sine x. Then the derivative of minus sine x is minus cosine x. Similarly, we take sine x, we differentiate it, we get cosine x. Derivative of cosine x is minus sine x. As for f of x, recall that you have to write your ODE in standard form before defining what f of x is. So in this case, the ODE is already written in standard form, so f of x is equal to tan x. We know that this system of 3 equations, 3 unknowns has a unique solution, and we're gonna find it. Uh, you can solve it whichever way you like. I would start by using the second equation, and I'm going to write u3 prime in terms of u2 prime. So u3 prime is going to be equal to tan x times u2 prime. Then I'm going to take u3 prime, I'm going to plug it in the third equation in here. So instead of u3 prime in here, I'm going to replace it by tan x u2 prime, and then I'm going to take common denominator, and I'm going to get minus cosine squared minus sine squared x over cosine x. This is nothing but minus 1. So u2 prime is going to be equal to minus tan x times cosine x, which is minus sine x. So we have found what u2 prime is. Then we can plug it in by this equation to deduce what u3 prime is. So u3 prime is going to be minus sine x times tan x, which is minus sine squared x over cosine x. So we're done with u3 prime, u2 prime. We need to plug them in the first equation to find what u1 prime is. So u1 prime is going to be minus cosine x times u2 prime, which is sine x cosine x, minus sine x times u3 prime, which will be equal to sine cubed x over cosine x, which after we take a common denominator, I'm gonna get sine x cosine squared x plus sine cubed x. If I factor out sine x, I'm gonna get sine x into cosine squared plus sine squared, which eventually is gonna be equal to tan x. So we have found what u1 prime, u2 prime, u3 prime are. Now I need to integrate those three equations to get what u1, u2, and u3 are. So u1 is the antiderivative of tan x, which is some constant c4, minus the antiderivative of sine x over cosine x is ln of absolute value of cosine x. u2 is the antiderivative of minus sine x, which will be some constant c5 plus cosine x. And finally, u3 is the antiderivative of minus sine squared x cosine x. We already found the antiderivative in the previous example. This will be equal to some constant c6 plus sine x minus ln of secant x plus tan x, or you can write it in this form. As usual, we're going to assume that the constants c4, c5, and c6 are equal to 0 for simplicity. This will imply that our particular solution is u1 times y1, which is simply u1 plus u2 times cosine x plus u3 times sine x. So after we plug in the u1, u2, and u3 that we just found, the functions, and after we simplify, note that in here we're going to get sine squared plus cosine squared is going to be equal to 1. So we're going to get the following form: 1 minus ln of absolute value of cosine x minus sine x times ln of absolute value of secant of x plus tan x, or you can write it as sine x plus 1 over cosine x. So we have found the particular solution. Last step is to deduce the general solution of the inhomogeneous ODE. So the general solution yx is going to be the complementary solution plus a particular solution, which will be of the following form. Note that in here the constant 1 we could added, or if you want included in C1, since C1 is an arbitrary function. So I could have replaced C1 plus 1 by another constant, let's say C1 tilde. Or you can keep it in this form both ways give you the correct answer at the end whenever you're solving an initial value problem. Okay, because at the end, recall that you'll have to find out what C1, C2, and C3 are by plugging in initial conditions. Okay, so one last thing to note, uh, recall that in here we're assuming that x is between minus pi over 2 pi over 2. The reason we're considering this interval is because we need to make sure that our solution is defined, and ln is not defined for at 0, so we need to make sure that sine x plus 1 is not equal to 0. Moreover, cosine x, the denominator, cannot be equal to 0, similarly in here. And if we look at the interval minus pi over 2 pi over 2, then in this interval we are sure that cosine x is never equal to 0 and sine x is never equal to minus 1. So our solution is well defined over this interval, and even if you differentiate it, its derivative is going to be also well defined and continuous over this interval.